So here's another example using Euler's method. So here we want our interval to be from 0 to 1. We want to use 4 segments. We want to round to 2 decimal places. And here is the equation that we want to be able to, or the differential equation that we want to be able to solve. Okay, so again, the first thing that you want to be able to do is find h and g of x comma y. Okay, so the first thing that we want to do, so h is going to be equal to b minus a over n. B in this case, because it's between this interval from 0 to 1, it'll be 1 minus 0 divided by h, which is 4. That gives me 0.25. So everything is going to be going by 0.25. Our g of x comma y is going to be whatever's on the right-hand side of y prime. In this case, it's 4xy. Okay. All right, so now what we're going to do is we're going to make our table. So here's n. Here is x sub n. And here is y sub n. Okay, so we're going to start at 0. And then we want 4, so it's going to be 1, 2, 3, 4. Okay, so now we're going to start off at the very beginning when n equals 0. So when n equals 0, x0 and y0 is going to be whatever my initial condition was, which in this case was y of 0 equals 1. So that means x is 0 and y is 1. That's where we're starting. Okay, now what we're going to do is we're going to move over to the first segment. So that's going to give us x1. x1 is just going to be x0 plus h. Okay, so x0 in this case is going to be, we're starting at 0. I'm going to add 0.25. Okay, and what I'm going to get is 0.25. Okay, that's what I ended up getting. Okay, so now what I'm going to do is I'm going to find my y1. So the way that we find my y1, I'm going to take y0 plus g of x0, y0 times h. So y0 is just equal to 1 plus g, okay, that's just this guy. So that thing is just 4 times x, which in this case is 0. My y is 1. And then multiplied by h. And then h in this case is 0.25. So when I multiply this guy out, I'm going to get 1. Okay. So now I'm going to do it for n equals 2. So when n equals 2, I'm going to have x2 is equal to x1 plus h. x1 in this case was 0.25. I'm going to add it to 0.25, and I'm going to get 0.5. So my y2 is going to be equal to y1 plus g x1 y1 times h. So my y1 was the previous y, which is 1, plus my g of x1 y1 is basically plugging in x1 and y1 into the g, which is going to be 4 times 0.25 times 1, and then times my h, which is going to be this 0.25. So in this case, what I'm going to get is 1.25. Okay. So now my next thing is figuring out what n equals 3 is. So I'm in the third segment. So I'm going to have x3 is equal to x2 plus h. So x2 in this case is going to be whatever was before, so it's 0.5. And then we're going to add it plus h, 0.25. This is going to give me 0.75. So y3 is going to be equal to y2 plus g of x2, y2 times h. So y2 in this case was the previous y, which is 1.25. G of x2, y2 is plugging in the x2, y2 from the previous one into the g value. So it's going to be 4 times 0.5, and then multiply by 1.25, and then multiply by 0.25. So when I do that, I'm going to get about 1.88. And then I'm in the fourth segment. So this is going to be x4 is equal to x3 plus h. So x3 in this case is going to be my previous one, which was 0.75. I'm going to add it plus h, 0.25, which gives me 1, which is perfect because it should be from 0, starting from 0 all the way to 1. Okay, so now my y4, so this is where we really find our solution. We're going to take y3, add it to g of x2. Oops, that's wrong. x3, y3 times h. So y3 in this case was 1.88 plus, I'm going to multiply 1.88 and 0.75, plug it into the g. So you're going to have 4 times 0.75 times 1.88. Multiply this by the h, which is 0.25. And what I end up getting is 3.29. So this is actually my final answer. Okay. So if I were to go ahead and collect all of these points, notice that I first start off with 0, 1. Then I go to 0.25, 1. Then I have 0.5, comma 1.25. Then 0.75, comma 1.88. And then 1, comma 3.29. Okay, so basically if I were to draw these out, you will kind of have a line segment. Okay, so you'll have these segments, okay, that you can connect them, and that will be really close to the true solution. Now actually, if you go ahead and get this differential equation, you actually can figure this out using separation of variables. And actually the true value, what really y is just e to the x squared. Okay, so this is actually the truth. So if you were to use separation of variables, you actually can figure out what the value of y is. So now let's go ahead and see, how does this true value, so we know that this is a true value, how do these points approximate this true value correctly? Do these points give you a really good approximation of the true value, or is this just not good? Okay, so what I'm gonna do is that I'm gonna go ahead and just use Desmos to try to figure out what the exact value is and see if our approximation is good enough. So the first thing that I'm gonna do is I'm gonna write down the true value. Okay, so y is equal to e to the x squared. Okay. Oh, that didn't quite do it. Okay, so let me try this again. So let's do, so the true value is y is equal to e to the power of x squared. So that's basically what the true value looks like. So it looks like that, kind of looks like a parabola going really, really fast. So now the points that we found from Euler was 0, 1. So that was my first point. Then we have another point, 0.25, 1. Then we have another point, which is going to be 0.5, 1.25. And then our next segment is just 0.75, 1.88. And then our last point at 1 was just equal to 3.29. Okay, so the whole point about this is that these points should be very, very close to the true value. Well, this is the true value. Let me zoom in a little bit. You can kind of see that our points are pretty close to this true value. So the red one is a true value. These were all the segments that I made. So here's a segment. So here's the first segment. Then from here to here, another line. And then from here to here, another line. So you can see that it's kind of close. It's not the best, but you can probably imagine that if our step size was smaller and smaller, so if our value of h was much smaller, and we had many more segments from 0 to 1, then this approximation will be much, much better. So this is kind of a little visual of what exactly we're doing. We're just trying to approximate the true solution that which we don't know with just these line segments. So that's basically the whole gist of Euler's method. So it is a complicated process because there's a lot of, it's really easy to get confused with all of this work. So if you look at all of our solutions, you can see that it can get really, really complicated really quick. So especially if you have a lot of a lot of segments. But luckily we have computers now that can do this for us. But at least you'll able to do one problem and see what exactly how this is basically solving the differential equation. So here's a solution, and that's basically it for this one.